Okay, guys, I'll just turn on my camera there. I'm sorry, I can't see you, but can you guys see me? Yeah, there you apparently you can see me. Okay, so today's asynchronous assignment is going to be, it's going to go through some questions in the back of the book this time. Page 41 is where I'm going to start. I haven't gone through these yet, so there's going to be a lot of pausing of the image or pausing of the video, though that should go fairly seamlessly for you guys. Yeah, so anyway, let's get started. So I'm going to share screen. There. I'm going to turn this off because I'm flipping it over. It's just going to face the ceiling anyway. I don't want you guys seeing my ceiling. No, I'm just kidding. Okay. So let's see, page 481. Well, I probably don't have to write a slide down. Let's see. Number 275 is where it starts. Which component of an electron system is made up of lead zirconate titanate, P, Z, T? Okay, so that, as we know, is the element, active element, crystal, ceramic, the ringy thing, the piezo. Sometimes people just call it piezoelectric too, but that's not one of on our list. So it could be any of those. Looks like letter B, transducers, active element. Okay. Number 276. I started working this one out, and I realized the answer is you don't have to work it out. How thick is the active element of a 3 megahertz pulsed wave transducer? It's 1/2 a wave length. Let me draw that out. I did this before, and it's kind of hard to do. So let me draw this out. Fortunately, I could turn my computer sideways so I could try to draw this. As a wave is created, half of let's say one cycle. Half of one cycle is created when the element expands. The other half is created when the element contracts. And that's what a vibration is. It's a expansion contraction. Now, we're talking very tiny expansion contraction. It would be invisible to our eyes, but it does happen. So if we kind of think of, let's see, if this is half the wavelength there, and the other half is there, we could say that this part of the wave here is still hasn't been created yet. It's still in creation. Well, let's continue this on a little bit longer. Okay, more or less like that. And so we could say that, let's see, since this looks like the beginning of a wave, we'll say that's the expansion portion. You know what? Just because it's really bothering me, I'm looking at everything sideways here. Okay, that was bothering me because I'm holding this computer sideways, and from my perspective, it was just not right. Okay, we'll call this expansion, or the part where the part of the vibration where this element actually got a little bigger. It was like actually widened out. And then this part would be more of the contraction. When I say expansion and contraction, I'm talking about the element itself. So in other words, expansion would be similar to the, well, you know what? I'm kind of going off into a region that's not going to help you for this test. Anyway, this was the expansion. This is more of a contraction of the element. So, but in any case, 1/2 of a cycle, or 1/2 of a lambda, 1/2 of a wavelength is the answer. Let's just quickly, how would we figure out what the actual wavelength is though? Okay, so, the thickness of the transducer, of the element for a 3 megahertz transducer. So wavelength, let's see, microsecond over frequency in megahertz. So, which is the same as saying 1.54 microsecond divided by frequencies 3 hertz, microseconds, megahertz, go away. 0.5 something, which is fine. That's the wavelength. But the answer to this thickness, that thickness is 1/2 of that, which would be 0.25 millimeters thick, 0.25 millimeter thick element, thick, this dimension. This dimension determines frequency, or I'm going to also say frequency sub zero, not zero, operating frequency is determined by that. It's also called the center frequency. It's the happy place for the transducer. Or if I'm, let's see, does this ring? Nope, that's more like a, anyway. Okay, let me pause here for a moment since I don't even know what the next question is. Okay, 277, true or false? The purpose of backing material of an ultrasound transducer is to shorten the pulses, thereby creating images with better image quality. Absolutely, positively, yes. Just found out a minute ago that this little coffee cup I have is not much of a ringer, but sounds horrible, right? But that is the type of sound we get from a transducer. So let's just draw some components of a transducer. We have the element. I don't know why my element's green, but it is. We have case, I guess. This is getting a little sloppy. Let's see, what else do we have, guys? We have a backing layer. This is really kind of a sound deadening layer. And then we also have a this guy here, that is, I can't think of the term. Oh, for God's sakes, Kurt! I gotta look up something I could literally repeat in my sleep. Matching layer. Ay, Kurt. Case. Well, let's see what else. Okay. So yes, but this backing material here is designed to keep the element from ringing. We want a very, very short ring, 2-3 cycles at the most. The reason we want that, shorter ruler, small ruler, you measure small things. No yardsticks allowed. Okay, page number 278. The main purpose of a transducer's case, well, I don't know. Case of the transducer protects the patient from electrical shock and internal components from damage. Well, yeah, I mean, that's what most cases do. That's a stupid question. Trust me, that's not going to be in the SPI. Which component of an ultrasonic transducer is made of a slab of epoxy embedded with tungsten particles? I don't remember them saying that tungsten particles were a slab of epoxy, though. I mean, okay. Epoxy, almost like a dense rubbery material. The damping material, that was the other word I was looking for. Epoxy, damping material, or backing material. I'm going to read, let's see, backing bonded. Oh, yeah, it does say right here. I didn't mention this when we went through this. Commonly made of epoxy resin impregnated with tungsten filaments. When the electrical spike excites the PZT, the backing material restricts the extent of the PZT deformation. And so, by the way, let's see, that causes quality, or the Q factor, quality goes down. If we could hear it, it would be an ugly, ugly sound. But that also, in making the quality go down, the number of cycles, in other words, the amount of time or the amount of the number of cycles that are produced goes way, way down. So it's like 2 to 3 rather than hundreds and hundreds of cycles of a normal crystal ringing. Okay, moving on. 279 compared, oh, no, that was it. 280, true or false. The characteristic impedance of acoustic gel is greater than that of the matching layer's impedance, but less than the piezoelectric element's impedance. Okay, so let's just think about this. We're going to add another layer of gel here. Let's see, what does gel look like? Gel is going to be kind of an ugly yellow here. Okay. Well, let's think about the reasons for what we have here. Excuse me. And the damping material is there to stop the ringing. The element does the ringing, but now because of the damping material, only 1 or 2 or 3 cycles are rung before it is completely muffled out. We call it the muffle layer. This is our matching, and then here is our acoustic gel. The problem with the element to the skin level, we'll just call it tissue, is that the impedance difference is so great that, remember what happens, large impedance difference, very large impedance difference, sound comes down, sound bounces away, and very little makes it through. Not a good thing. So the matching layer is a impedance that is less than the element, still greater than tissue. It's a step down. It's like literally walking down some stairs. Sometimes elements come with multiple matching layers too for more treads on those stairs in order to step it down. The acoustic gel, you could imagine, is another set of stairs on that. So if we think of it like that, it's like step, step, all right, big step, and then down into the tissue. You want to make those steps. If you don't make the steps, you're opening up the door and you're falling into the basement. That's not good. And then you're bouncing back because if someone left a mini tramp down there, you bounce right back up. No, so that's not good. We want to step down. All right. So false, the acoustic impedance of gel is lower than, so yeah. So you know, high, medium, low, lowest. Okay, so impedance, as far as impedance go, high, medium, low, lowest is kind of a, it's a steps down. Okay, let's get rid of some of that stuff. I have a feeling. That's as far as I can go. Okay. 281. The impedance of a transducer's matching layer is 2.6 megarails. And the impedance of the piezoelectric crystal is 3.4 megarails. If it is assumed to be a good imaging system, what is the best estimate for the impedance of the skin? Okay, so we're stepping down. What's going on here? 3.4 mega, oops. Did I spell? Yes, I spelled rails wrong. 3.4 is the crystal. And then we take a step down into 2.6 for the matching layer. 2.6 for matching layer. And then it's asking directly about the skin, so we'll skip the acoustic layer. But 3.4, 2.6, I haven't looked at the numbers yet. Maybe 2.0, maybe 1.8, something like that, right? So A, 1.5. I said 1.8, 1.5. There's an obvious 3, 2, 1. Blast off. All right. Number 282. True or false? A piezoelectric crystal of a transducer typically has an impedance higher than that of the skin. Yes, like 20 times higher than the skin. Okay. 283. Which of the following lists orders the impedance from highest to lowest? Okay, so we already mentioned this is the highest, medium, low, lowest. So let's see, does that show up? PZT, PZT matching layer, gel skin, letter D. So letter D is the one that works there. Okay, 284, what is the thickness of the matching layer of a 2 megahertz pulsed wave transducer? That's the same question. Half the width. 284 is basically the same question. It's before they asked for 3, now they're asking for 2. But it's half the wavelength of the sound. That is the same. Dang it. That's the same thing as we already talked about up here. Don't know why they did that. All right, let me pause and. Okay, number 286. The damping material helps to decrease the pulse repetition period achieved at a given imaging depth. Before you answer, probably following along, you can see the answer right here, but before you answer that one, that's a good one to read. If you zoom through this really quickly, you'll be like, damping material helps to decrease the pulse. Yes. Repetition period. No. Pulse repetition period is actually created by the machine. It's actually there's a part of the machine called a pulsar, which is determined by depth. And if you're in Doppler, then you have some control over that too. But so it decreases the pulse length, the pulse cycles, but not the pulse repetition period. So be careful. 287, vacuum material helps to decrease the duty cycle at a particular PRF. Ooh, yes. Why? Duty cycle, a particular pulse repetition frequency. Okay. Why would that be? The duty cycle. Duty cycle. Why are they using the term duty cycle? That's not what we've been using. Anyway, yeah, duty cycle. Well, that's really duty factor, right? Okay. Well, so duty factor or duty cycle is the percentage of time talking, right? That's basically our duty factor. The backing material helps to decrease the duty cycle at a particular PRF. Okay. So what if the backing material was ineffective? And we had, let's just, what if we had an ineffective backing material now the duty factor percentage of time has gone way up. Make sense? All right, number 288, pulse duration is increased as a result of the presence of backing material. No, that's exactly, this is pulse duration. It has gone up. It has gone up due to ineffective or backing material. And if we have good backing material, then the pulse is short. 289, backing material decreases the quality factor. That is true. Oh, there was something I wanted to show you guys. Here, let me pause because it's just better you don't watch me do this. Okay, and this is just an illustration. It's not necessary, but I figured I'd throw this in here because I regretted not doing this during our regular Zoom class. It's in regards to a low quality or a low Q factor. And so we did talk about bandwidth. And so with a low quality sound, as in, that's my coffee cup here. That's a low quality sound. If we could actually see the waveforms coming out of that, well, it might be short, like I've drawn down here, but then there might be superimposed upon that another frequency that's blue frequency had a slightly longer wavelength, so therefore not the same frequency. Perhaps there was a higher frequency, so that green wave there shows a higher frequency, a shorter wavelength. And we can continue to do that a number of times. And what we end out with is a mess. This is an ugly mess, but this is a wide bandwidth. This is broadband in a sense. And so what engineers are able to do is extrapolate specific waves out of that and say, we're gonna strike the transducer in such a way, with such a voltage, that it really maximizes perhaps this wavelength or frequency. Let's just say frequency, because it's a multi-frequency transducers, right? Or we could say, no, we want to go with a higher frequency. So this is how we're choosing to both strike the element with specific frequency of voltage to maximize. Because let's say the very first one I drew, this guy, let's say that's operating frequency. That's the happy place. That's where it wants to be. But because of the backing material, all these other frequencies exist. Since they exist, the engineers have figured out how to accentuate certain aspects. So they might say, well, let's go with a lower frequency. Let's go with a higher frequency. It can't go too far. I can't suddenly say, I want this frequency out of it. That's not going to happen. It has to be within a certain range. It's usually within a few numbers of the operating frequency. So that's just another illustration that I didn't show you before. Okay, let me pause again and get out of this. Number 290, page 484. The spatial pulse length is decreased with the application of backing material. Yes, that's the whole point of it. 291. Assume that the frequency of sound with the greatest power emitted by a transducer is 5 megahertz. The frequency of sound with the greatest power, that's kind of a weird sentence, emitted by a transducer is 5 megahertz. However, the pulse contains acoustic energy with frequencies as low as 3.5 and as high as 6.5. What is the bandwidth of this transducer? First of all, that was an accident. I just kind of showed you what that illustration might look like. But we really didn't talk about the bandwidth of the pulse. I feel like the questions here, but did we talk about that in the book? Well, let's go straight to the answer. The bandwidth of a pulse is defined as the range of frequencies that are present. To calculate the bandwidth, subtract the lowest from the highest, and the bandwidth would be whatever that number is. So let's see what they said. 6.5 was the highest. 3.5 was the lowest, so 6.5 minus 3.5 is 3 megahertz. In other words, darn it, now all right, I'm gonna pause, grab that. Okay, guys, here we are again. I just redrew my little mess. All right, so I've redrawn my broadband pulse here, a pulse with many frequencies buried within it. And gosh, I don't know what my center frequency, which color that is. I think green looks like it's about so the green is the color, is the closest color to the frequency center. In our case, frequency center frequency, the happy place is 5 megahertz for this question. And then, so that would be, well, right about there. That's the center frequency of 5 megahertz. This is really bothering me. What an ugly 5, huh? Good morning, babe. No, I gotta go in for lab. Wait, no, there's no lab. I'm actually doing lab right now. I'm recording, so my students are hearing our morning conversation. Okay, so 5 megahertz is the center frequency, the happy place frequency. This question says that it's as high as 6.5. So as high, well, okay, we have some numbers over here, but let's just say 6.5 is, let's see, what was my highest frequency? I think it was red. Let's see. That'd be the 6.5. And so let's just say that's right about here. 6.5 megahertz. And let's see, my lowest was definitely that purpley bluey. That one was my lowest. And put that right about here. And, what was that? 3.5. Okay, so this is my band width. .5 minus 3.5 is equal to 3 megahertz is the bandwidth. That's just simply the width from one side to the other. That's not a specific band that we're going to be using, in fact, because the lowest is 3.5. The highest was 6.5. And yeah, there's some extra stuff out here that is just unusable to us. When we look at this as a bell curve, this is well, they said it in the question. Assume that the frequency of sound with the greatest power. Well, that's basically what they're saying here. That is the greatest. I am the greatest. All right. That's the greatest. These are relatively weaker, but still usable. There might be other frequencies that are even higher, very weak. Let's just pretend that we know what this number is. Let's just pretend that this right here is, I don't know, 10 megahertz. But that 10 megahertz probably does exist over here. Here, I'll draw it in. 10 megahertz would be really high frequency. But, oh, let me draw it in again. Not only would it be very high frequency, but it'd also be weak. So unusable. So these are the usable frequencies here. Anyways, I'm going really off into the weeds to answer this simple question right there. All right, what is next on our list of things to talk about? True or false in general, ultrasound imaging, lower quality factor. True, damping materials secured to piezoelectric material, which is not consequences attachment. I'm going to skip that. I think that's easy enough. Here, let me pause so you're not listening to me. 296, page 485. Which properties of the piezoelectric crystal or element or whatever, active element, or ceramic of a continuous wave transducer result in the highest emitted acoustic wave frequency? Let's see, thin, high propagation speed, thick, thin, none of the above. Okay, A, B, C, D. All right, so far, remember, thin, thick. Okay, so far, let's see, high frequency, this is going to be the higher frequency. High frequency, low frequency, and I should have read this a little more carefully. Let's look at the answer here. So which properties of the piezoelectric of a continuous wave transducer occurred? Okay, continuous wave transducer. The frequency of sound emitted by a continuous wave transducer is determined only by the frequency of the electrical signal that excites the piezoelectric crystal. Okay, let me finish. The crystal's thickness and propagation speed do not affect the frequency of sound from a continuous wave transducer. I find that hard to believe, but basically what he is saying, on a continuous wave transducer, I'm going to put this sideways. There is a, let's see, here's my wire coming in. Okay, yeah. Let's make the color of electricity red. There is a constant these are basically electrons or a voltage coming through at a specific frequency of voltage or frequency of electrons, ends out creating the same frequency of sound. Let's just say it's this frequency. And you son of a... And according to the book, on a continuous wave transducer, the width and speed of sound in the piezoelectric doesn't matter. Well, come on. In my opinion, there is still going to be a happy place for that transducer. They're not going to make this element at any size they want just because they're going to, there's still going to be a happy place. So they're going to be working around the happy place. But according to the book, yes, that frequency of electricity is going to be the frequency operating. So what goes in is what comes out. On our pulsed transducers, it has everything to do with the width of the transducer itself. So there you go, Kurt. Don't read the question, get it wrong. So it really doesn't, oh yeah, let's see. What helps determine the frequency of the sound produced? Yeah, okay. Okay, I just wrote this down, and I realized, and I can't go back. I would have to start all over again. I can't fix what I said wrong. So it's just a semantics, but the semantics matter. Thickness, Kurt. Width is what really most people would consider this width, right? So I'm very sorry about that. Thickness. All right, let's go down to this question that I was just going to look at here. Well, I'm glad I caught myself. Better late than never. 299, I like this. An ultrasound pulse is traveling in soft tissue. Which of the following is most important in determination of the frequency of sound? We have some information there that is not necessary. An ultrasound pulse is traveling in soft tissue. Which of the following is most important in the determination of the frequency of sound? The fact that it's traveling in soft tissue has nothing to do with it. The frequency is created by, let's see. Speed of sound. Ugh. Ugly. Speed of sound in the element. And 2 times the thickness. So why 2 times the thickness? We've already shown you. Basically, there's 1 thickness, there's 2 thickness. One, 2. Ooh, that was messy. Okay. Speed of sound. So if the speed of sound goes up, wavelength goes up. Oh, and 2 times thickness is the equivalent, really the same thing as saying lambda, the speed of sound, over frequency. So let's see, speed of sound. Oops, wrong F. Okay. So what else do I want to find? If I want to find frequency, it's C divided by lambda. So frequency is equal to C divided by wavelength, which is also the same as saying 2 times the thickness is equal to C divided by lambda. Anyway, so that's different ways of writing the equation. Let's look at, and the last way of writing the equation, let's just do, just use this guy here and this guy over here. If we say, if we want to solve for C, it's this guy. So C is equal to lambda times frequency, or C is equal to lambda times 2 times the thickness. Okay, so let's go back to the question. I think I've answered a whole bunch of questions that were not asked. Well, I have. I've asked a lot of questions that were not asked. Hopefully this all wasn't too much, but I just kind of wanted to show you how to be able to take a very simple equation and manipulate it around to sometimes answer different questions. But in any case, which of the following is most important in determination of the frequency of sound? So frequency of sound, or right, frequency of sound. So the propagation speed of the transducer. Oh wait, which of the following is the most important in determining the frequency of sound? Two characteristics that determine this frequency of sound of pulse are thickness and the propagation speed in the crystal. The speed and impedance of the matching layer and the thickness of the backing material are unrelated to the frequency of an ultrasound pulse. And the speed and impedance of the matching layer and the thickness of the backing material . Oh, I see. So, okay. It's just a matter of when you look at A, B, and C, the propagation speed of the ultrasound matching material, and that doesn't have anything to do with it. The thickness of the backing material, nope, nothing. Letter C, the impedance of the transducer's matching layer, nope. So D is the only question that has part of the answer. It has D, says this propagation speed, so it has this part of the answer. Really, it's both. Whoops. Well, yeah, it's both. But anyway, only part of it is used. Oh no. Okay, time to pause. Okay, I want to keep moving at this. Sound beams, page 487. 304, what is the region of the transducer? The smallest cross-sectional area of a beam called, okay, let's keep doing this, that. What is the region? So here's the smallest cross-sectional area of the beam. This is all beam, except for this, of course, this is element here. Let's see, well, okay, so what is this section called? That is the near zone or Fresnel zone. Let's not write it down. Let's keep moving quickly. Question 305, what, the area that starts at the beam's smallest diameter and extends deeper. I see how he says this. I don't think he even knows what he's talking about. He's very careful, usually not to say exactly where this ends. So we're just going to say from here to here for now. And that, of course, is the FAR zone or the Fraunhofer zone. So, which of these terms have the same meaning? I'm just going to, Fresnel zone is also the near zone. Fraunhofer zone is also the FAR zone. The focus is where this basically, we're going to say right there, the focus is right here at the narrowest. What else can we say? I'm just going to skip ahead here. We got a little, this is a little, the size of this zone is, kind of depends on a lot of things that we don't need to worry about. But basically, it's this whole zone in here. That is the focal zone. And kind of from here to here is the near zone length. Okay. What are these questions on page 489? Or did I miss anything? Small as all the following are true of the focus except, yeah, it's not located at the Fresnel zone, at the end of the Fresnel zone. And by the way, and I've mentioned this before, there's no way to focus, if this is your natural focus there, there's really no way of bringing the focus further down. You can focus it closer and closer and closer. You can change the focus either by external element or external focusing, like that, internal focusing, or even with a multi-element transducer, electronically focusing. You could only bring focus closer. You cannot focus in the far field. However, most elements are designed so that the natural focus is quite deep, so that you never really have to focus in the far field. Let's see, here's okay, just go on. I'm just going to go through 309 through 317 quickly. The near zone is the only region where the diameter of the sound beam is smaller than the transducers. The near zone is the only region where the diameter of the sound beam is smaller than the transducers. Well, I would say everything up until, let's see, so here's my original aperture up here. That's my, at 2 near zone lengths. Let's see, let's do it. Well, 2 near zone. See, here I am. I keep drawing my beam a little bit off. So that should be 2 near zone lengths. So in other words, 1, 2. I didn't draw that very clearly, but or very accurately, but you get the idea. So everything from after the aperture, it's immediately getting smaller. And then after the focus, it starts to widen out, but it's not until 2 near zone lengths that it's equal to the aperture. Aperture. And then down here, it's greater than aperture. And then it continues to just go spread out, spread out, spread out, spread out. Far zone is the only region where the beam diameter exceeds 311. If the diameter of a sound beam is 8 millimeters at a depth equal to twice the near zone, then the PCT crystal has a diameter of 16. False. No. If this is 8, because it says at the diameter of sound beam is 8 millimeters at the depth of equal to twice the near zone. 2 near zone lengths is 8 millimeters. Then this is 8 millimeters width aperture. The diameter of the acoustic sound beam produced by crystal is 8 millimeters at the depth of twice the near zone length. And the same question. 313, the near zone is the only region where the diameter of the sound beam decreases as depth increases. Yeah, that's a good way of saying it. The diameter is decreasing as the depth is increasing, and that's only happens in the near zone. Um, 315, the higher the frequency of the acoustic wave, the shorter the length. No, and that's kind of tricky. That is definitely a bit of a tricky thing. Let's say high frequency we'll say this one was a low frequency. So if a high frequency, the it's going to have a longer focus, a deeper focus, which goes against common sense because we already know that high frequency doesn't go that deep to begin with. But its focus is deep. Go figure. The greater the diameter of the transducer's piezoelectric crystal, the longer the near zone length. That is true. Now that makes physical sense. That makes physical sense. So if I'm gonna make a wide diameter, now I can't even fit this on the, I won't be able to fit that on the screen anymore. Oh dear. Okay, well anyway, my focus is now gonna be more like down here, wide, very wide diameter. Let's say wide diameter and high frequency, so that was a very low. What 318 for this shape, producing continuous sound, which design will create a beam with the shallowest focused. Okay, shallow. Oh, you son of a! It got me again. It's number 318. It got me again. I'm not paying attention, and this is what happens to all of us, students and teachers alike. For a disc-shaped PZT crystal producing continuous sound. In other words, a continuous wave transducer, which will create a beam with the shallowest focus. A continuous wave transducer producing the shortest near zone will have a small diameter and a low emitted frequency. Oh yeah, okay. I'm sorry, in this case, continuous wave doesn't make a difference. It's still a sound beam. And so, let's see what shallowest focus. Well, shallow focus. If for a shallow focus, we do not want high frequency. We do not want a wide diameter. We want a narrow diameter, a narrow width, a narrow aperture, and a lower frequency. Let's see. See, now that's throwing me off. I'm going to skip 319 because it's really the same. Two ultrasound systems are identical except the diameter. Two systems are identical except for the diameter and aperture, diameter, width. All of those are the same. Let's see. Where am I? So 320, the one with the larger diameter crystal will have the deepest focus. We're just kind of repeating ourselves here. In fact, let me pause and get to a better question. Okay, guys, I actually have to prepare for class today. So I'm just going to say one more thing. On 322, the sound travels deeply into the far zone, the beam diverges or spreads out. Which of the following will result in the minimum beam divergence deep in the far zone? Okay, just remember these two shapes. There. Actually, let's use a little cheater here so I can do this without being too ugly. All right, well, it is what it is. Still not a great picture. But the point is there, I think. The point being, anytime that you bring the focus closer, the far field spreads out faster. Anytime you bring the focus deeper, the far field spreads out slower, not as fast a spread. So, wide aperture, high frequency is going to have the least amount of spread, and that's a good thing. If you're trying to image the far field, that's a good thing. Small diameter, small aperture, low frequency is going to be, well, it's going to have the most spread in the far field. And so that's not helpful. Okay, that's all I want to talk about today, guys. There's a few questions left. I probably could go through them, but I need to get ready for class, and you guys have sat here long enough listening and hopefully taking notes and working through these as well. Anyhow, I will see you later.